My guest today is John Parmentola.
Thank you, Tom, for inviting me to give this talk. In terms of my background, I've basically worked in every sector within the U.S. national R&D enterprise. I started out as a researcher in basic research in high energy physics, where I spent a considerable amount of my career trying to understand the nature of neutrons and protons and particles that are related. And then I transitioned into nuclear physics for a while, and then I worked in the interface. I've been a professor. I've taught undergraduate school physics. I started a basic research program from scratch. Also, during my time at M.I.T, I got involved in science and technology policy, namely defense issues. And I did some early work on what later became known as Star Wars, the Reagan defense program. This predated Reagan announcement of the Strategic Defense Initiative. That followed me around during my career. And I eventually transitioned into science and technology policy. I went to the Kennedy School for a couple of years. I worked with the late Ashton B. Carter, who was former Secretary of Defense, who unfortunately passed away last year. And then I got some sort of semi-government experience at the M.I.T Corporation, and then I transitioned into government and worked in a number of agencies, Department of Energy, the U.S. Army. I helped stand up the Defense Threat Reduction Agency, and I did some interesting work there for President Clinton on the Comprehensive Test Ban Treaty. I then went back to the Army during the Second Gulf War, and I worked there at a high level as a senior executive, leading the Army's basic research and applied research programs, as well as laboratory management. And there I did a wide range of things. One in education, another I came up with the idea of the world's first robotic dog that could see and sniff explosive, and I led the development of that. It saved lives in Iraq and Afghanistan. I launched 5 research centers across the country, one of which was a collaboration between the U.S. and the United Kingdom. And those research centers have been very productive in terms of how they've contributed to the Army science and technology base. One member of one of those centers won the Nobel Prize in chemistry. She was the 5th woman in history to win the Nobel Prize. And Frances Arnold, very gifted and talented person who I funded her early work in what's called directed evolution. And another center won several Academy Awards and technical awards in cinematography. And then I transitioned into the private sector. I worked at General Atomics as senior vice president for energy and advanced concepts. And I retired from there. And so, which brings me to one of my interests, which is ice ages. So a number of years ago, I decided to try to learn what I could about ice ages, which brought me to what people call Milankovitch theory, Milankovitch cycles, named after a Serbian mathematician and astronomer who about 100 years ago began to think about how the Earth's motions could affect the Earth's climate and actually cause ice ages. And he made a hypothesis, which you can describe in various ways, But basically, he speculated that because of the Earth's motions, there can be a reduction in sunlight at northern latitudes. And by northern latitudes, he was focused in on roughly around the Arctic Circle. And the reason for that is there's a large landmass there where snow and ice can accumulate. And so as the sunlight decreases, that can provide the opportunity for snow and ice to accumulate. And if that happens, you can change the Earth's albedo, which means that more sunlight is reflected away from the Earth, which can lead to a temperature descent. And as that temperature descent increases, that can accelerate the formation of ice sheets and snow accumulating, which further enhances the albedo and so on, and it drives the Earth into a glacial period where it's extremely cold. Now, people refer to Milankovich's theory as a theory, but my opinion, it's not a theory. It's a hypothesis. And the reason why I say that is its predictive value is limited. My work, which I'll discuss today, mainly deals with certain synchronizations of the Earth's celestial motions and how they manifest themselves in what's called paleoclimate data. During Milankovich's time, there wasn't paleoclimate data of the sort we have today. That took many decades of dedicated work by many, many people to try to compile this data. If the listeners want to learn more about my work, it's published in a new journal called The Science of Climate Change, which I've indicated on the first chart. And all the computations that I will do today follow from a website that was created by Jacques Laskar and his colleagues. That is a remarkable website where you can calculate and reproduce every calculation I will present today. Getting back to this issue of whether Milankovitch is a theory, I think the best way to explain why it isn't is on the next slide. The method we use to try to establish objective truth is the scientific method in physical science. All the knowledge, the reliable knowledge we have today is a result of this method. Its first presence historically is that of Galileo Galilei, who published a description of this in 1623. And of course, he's one of the more successful practitioners of using this method. This method has been used over the last 400 years, and it not only contributed to science, it also inspired the Age of Enlightenment, which also led to the founding of this country. It accelerated our acquisition of objective truth over the period of the modern world and accelerated the advancement of science and technology. Now, the method is rather simple. And my favorite description of this is by Richard Feynman, who is one of the greatest minds and teachers of the 20th century. So I'll just read it and comment on it. So he's speaking to an audience of students. And there's a video associated with this on YouTube. He says, now I'm going to discuss how we would look for a new law. You can replace new law by new phenomenon. Doesn't matter. So in general, we look for a new law by the following process. First, we guess it. Of course, the audience laughs. And he says, no, don't laugh. That's the truth. Well, that guess is a hypothesis. And then we compute the consequences of the guess to see what if this is right, if this is law, we guess is right, to see what it would imply. And then we compare the computational results to nature, or we say compare to experimental experience, compare it directly with observations to see if it works. So implicit in all of that is first you make this guess, and then you have to translate it into mathematics. And then you use that mathematics to make predictions of quantities that relate to experimental measurements. And you have to compute them at an accuracy level that's consistent with what experiment measures. Also implicit in all this is that the experimental data is valid. In other words, it's been reproduced. People confirm that the measurements are measurements of what you think you're measuring, and the accuracy has been validated. So then it comes to the next paragraph, and he says, if it disagrees with experiment, it's wrong. In that simple statement is the key to science. It doesn't matter, it doesn't make any difference how beautiful your guess is, it doesn't matter how smart you are, who made the guess, or what his, or I would say her name is. If it disagrees with experiment, it's wrong. That's all there is to it. So implicit in that is that if it disagrees, it then dismisses your guess or your hypothesis, or it requires you to modify it and then proceed again through the same process. And you proceed over and over again until you either give up or you actually confirm that your hypothesis is correct. So the data feeds back on the hypothesis. So it's a nonlinear system. It's not linear as some people seem to think. It's actually nonlinear, and you go through this over and over again. Milankovich's theory doesn't satisfy the scientific method. I will attempt to use it in this talk. So the Earth's response to the celestial motions manifests itself, presumably, in paleoclimate data, which is a time series. And it's it's proxy data in the sense that you don't directly measure, say, the Earth's temperature. You measure, say, an isotope in an ice core, its concentration as a function of time. To the right, you see what's called Epoca Dome C ice core data from Antarctica. And it starts at 0 to the right and goes back in time 800,000 years. And all of this data has been compiled, and then it's been modeled in that the proxy data has been transformed into a temperature scale. And that temperature scale is along the vertical axis to the left, which is in degrees centigrade. And 0 corresponds to the average global temperature, which is roughly taken to be 15 degrees C. On this, it's taken to be 0 and deviations from 0. You can see that these peaks that you see, some of them are below 0 and some of them are above 0. You might ask, well, should I take this temperature seriously? And my answer to you is no. It's model dependent, but that isn't the point, or at least my point, looking at this data. It has certain general characteristics. By the way, the peak that's to the right is the Holocene, and that's the one we're on now. But if you look at the data, what you see is certain kind of general structural features, one of which there are prominent what I call steep inceptions. These are the rises that occur on the left of these peaks. And then there are also steep terminations that also occur. And if you sort of study it a while, you come to the conclusion that these steep inceptions and terminations are on the order of 10,000 years. You would measure them based upon that kind of unit. And they vary, and I'll explain why they vary later on. But just keep that number 10,000 years in mind, because what it suggests is a common mechanism for why these occur the way they do. The warm periods, which are the width, essentially, of these peaks, ranges from 3,000 years to 22,000 years. So the range is pretty wide. You can see the very narrow one, which is, depending upon how you count it, the fourth or fifth peak from the right. It's very narrow and needle-like. And they get much broader as one there in the middle. That's usually associated with the Holocene, which is the one we're on to the far right. There's the one that is narrow, needle-like, and here's the one that's broad, and the Holocene is over here to the right. Okay, it's to the right. So anyway, in looking at this, you also see the gaps between the peaks. These are glacial periods that are very cold, and they vary in duration, and they're not periodic. By periodic, I mean with a fixed time period. They're all over the place. The fixed time period would be like 24 hours in a day or 365 days in a year. That repeats, although even those are not precise, but to a good approximation, they are. Here, it's much more spread out in terms of the duration. So, like here, you have one that's a very long duration here, right? You have others that are very short, like that over there. It's rather short duration. So you need some way of explaining these sort of general features. So when Milankovitch was talking about sunlight and its influence at northern latitudes, what he was really talking about is what's called the insolation. It's a peculiar terminology. Some people get it confused with insulation, which you use in your house. It's if you look to the diagram over here to the right of the Earth, it looks like a flashlight is illuminating it. And in reality, of course, that isn't the way it works. The Earth moves further away from the sun and closer to the sun because it's not in a circular orbit. It's an elliptical orbit. So the intensity of that sunlight, which people refer to as the solar irradiance, which is in watts per square meter, it varies in intensity because of the distance away from the sun. It also varies because that axis in red, rocks can point more towards the sun or further away from the sun. So these motions occur, and one way of thinking about it, it beats onto the solar irradiance, and that beating essentially winds up resulting in a distribution of that solar irradiance over the surface of the Earth. And that's what insolation is. It's a distribution of that. And you can think of the Earth as like an antenna that's receiving this amplitude modulated wave. It's an AM wave, like a radio wave. And the Earth is like a sensor, and it responds to it. So here on this slide, I'm comparing a prediction of the insolation, which you can basically calculate from Jock Laskar's tool, from minus 850,000 years to plus 60,000 years. And you can see it's a very complicated wave. And it has modulation. In other words, the amplitude varies from point to point in time. And then below it is the ice core data that I had on the previous slide, and I've labeled using the standard labels that are used for marine isotope stages. And so if you look at the top, you count the number of transitions there are between insolation minima and maxima over 800,000 years at 65 degrees north latitude during June or the summer solstice. There's 74 of them, of varying swings from minima to maxima. And below, you have 13, maybe 14, depends how you count them, prominent marine isotope stages, including the Holocene. So how do you reconcile this? Some of these, especially the very steep ones that you see that are broad, how do they relate to the insolation? So you can see certain amplitude changes like this one here, which goes from a deep minimum to a maximum. And then you can move over and look at this one, which is much more shallow in terms of the changes in the insolation, yet there's this gigantic peak sitting underneath it. And this is the peak that usually this one here, 11C. 11C is usually associated with the Holocene to the far right. So you say, well, why do some have longer durations than others, for example? And some even look split, right? So if you tend to look over here, for example, this one starts out 18D with a rise, lasts a while, drops down, and then moves back up again. You also notice in going from 18D to 17C, there's a temperature trend, right? It goes from a peak at 18D and then rises again up to, so there's some temperature trend associated. Well, what's the cause of that? Right? You see that also if you go over here, for example, to 13, similar kind of structure, and it's split. It looks like it's almost split. And you go over here to 7, the 7's over here, 7C and A. You can see, well, it's kind of split. I'm not going to talk about the splitting specifically in this talk. If you go to my paper, I go into that in detail. So there's several questions, right? How are the temperature trends sustained? And are some insolation transitions special, and why? Okay, why? Why is that? So you go back to basics and go to the Earth's celestial motions, right? So the first is what I would call a distance or radial motion. And the Earth's orbit over the last 800,000 years has been more circular. That's defined by eccentricity. If the eccentricity of the Earth's orbit is 0, it's circular. So you can see the value there, 0.0034. That's extremely close to circular. But it's also gone to 0.05, which is almost a factor of 20 difference in the eccentricity over the last 800,000 years. And of course, there, at one point, the Earth is furthest away from the sun, and then at another point, so here it's furthest away, and then at another point back over here, it's closer, right? The furthest point is called aphelion, the closest point, which I identified just a little while ago with the cursor, is perihelion. And so these distance changes causes the amplitude of the insulation to decrease at aphelion and increase at perihelion. The axis also wobbles because there's a torque being acted on. The Earth has a torque acting on it from the sun and the moon. And the axis wobbles around. It goes around in a circular path. Currently, it's pointing towards Polaris. 11,000 years from now, on average, and that statement is on average, it flips 180 degrees and it'll be pointing towards Vega, which is here. Be pointing towards Vega in 11,000 years or so. And so this axis goes around in a circle. This is called a precession. You see this dotted line in the middle. That's a line perpendicular to the Earth's orbital plane. And the angle of inclination of the Earth's axis with respect to the perpendicular is called the obliquity. Which brings me to the obliquity, which is the third motion. The spin axis rocks, okay, towards the sun, away from the sun. And that rocking motion is about 2.4 degrees. It's very small. It's 0.042 radians. It goes from an angle of 22.1 degrees to 24.5 degrees, and vice versa, on average, every 21,000 years, which is about double that of the precession. What this does is it moves the sun rays north and south, south to north by about 267 miles. Okay, so those are the basic motions that affect the insulation. However, those motions are cyclical, but they're not periodic. In other words, you can't associate a fixed period of time with those motions. At best, what you can do is define half cycles. In other words, it goes from a minimum to a maximum, and then from a maximum back down to a minimum. And those half cycles are not symmetric. They don't have a fixed period. So for the obliquity, on average, over the last 800,000 years, and you can do the calculations yourself, the average is about 41,000 years. But the half cycles, which you see plotted off to the right here, range from 18,000 to 23,000 years. So they're pretty widely separated. The precession, on average, is 21,000 years, but the half cycles vary all over the place from 7,000 to 15,000 years. This is why when I looked at the data, I picked out the time scale of 10,000 years. And when you look for these steep inceptions and steep terminations, and you look at it sort of as 10,000 years, they vary. And it's the precession cycle that is really at work. But how? That's the question. What is it doing? The third is the average eccentricity cycle, which is about 94,000 years. And the half cycles also vary widely from 30,000 to 70,000 years. So now, this, what I would call quasi-periodic behavior, is essential to making a time series comparison between any model you come up with regard to how these inceptions and terminations and structural features occur, and compare it with the data. They're essential to it. So one question you might ask is, what causes insulation minima and maxima? So I have here two configurations of the Earth relative to the sun. The top one is today. It's the current configuration as it goes around the sun over a period of a year. So what you can see here is to the left is the summer solstice, with the Earth's axis pointing towards the sun at aphelion, the furthest distance away. Because it points towards the sun, that tends to increase the amount of insolation at northern latitudes. Fast forward to winter, the winter solstice, which we just got through, it at perihelion with the axis pointing away. But it's closer to the Earth. 11,000 years ago, we just were at a peak in the insolation, and prior to that, we were in a glacial, and we came out of that glacial. The Earth-Sun system was in a different configuration. Back then, the summer solstice occurred at perihelion, where the Earth's axis pointed towards the sun, and then the winter solstice was at aphelion further away, a reduction in the insolation, with the axis pointing away. So in going from the bottom 11,000 years ago to the top, we went from high insolation during the summer solstice because the Earth was at perihelion pointing towards the sun to a minimum. The summer solstice, where the Earth was pointing towards the sun at aphelion. So I refer to this as a perihelion to aphelion transition between maxima and minimum. Of course, a similar thing occurs between aphelion and perihelion, where it then increases. Now, during this transition, there are two things that happen. One, the Earth's axis flips. Remember, on average, every 11,000 years, that axis flips its direction. So that's one thing that happens. The other thing that happens is the Earth's eccentricity changes. Okay? It can become more elliptical or less elliptical. In fact, what happened between 11,000 years ago down here and going to today, the Earth went from a local eccentricity maximum, and it's headed towards a minimum becoming more circular. So if you look at the diagram to the right, it started out with this purple trajectory, and it's moving more towards a circular one. In doing that, aphelion moves closer and perihelion moves further away. Okay, it's slight. It's not dramatic, but you can characterize these two aspects of the Earth's motion through one parameter called the precession index. And it also goes by the name of the climate precession. That's the terminology used by Jacques Laskar on his website. I refer to it as the precession index. It combines eccentricity and precession through one parameter. So what I have plotted here at the top over a period of minus 850,000 years to 50,000 years is the precession index, which you can see modulates. It's a precession modulated by the eccentricity being that outer blue curve that you see here. And below is the obliquity that goes from minimum to maximum. It oscillates. But again, it has no fixed period. So if you look at some of the annotations I have, so for example, here, you see this vertical blue arrow points to a precession minimum. So where it's negative. By convention, it's just purely by convention, that negative is associated with the Earth's axis at perihelion pointing towards the sun. It then, after a precession half cycle, goes up and reaches this arrow, this maximum over here that you see, the blue arrow pointing down. And you see that the eccentricity changes, but it changes very little, right? There are other points along this where the changes are greater, but you can just see here, it doesn't change very much. And if you look at the value, you go off to the left over here, it's about 0.05, okay? Just keep that number in mind for later, store it. Okay? If I look at the obliquity over a precession half cycle, it really doesn't change very much. So here on the axis on the left, here, this is the angle in radians. You see it starts out at about 0.415. And then after a precession half cycle, over here, it's down at 0.41. That's a change of 0.005, right? So that's an order of magnitude smaller than the eccentricity. Please keep these two numbers in mind, 0.005 and 0.05. Off here to the right is the state of the celestial motions of the Earth 11,000 years ago. So again, you see the precession here is negative, meaning this is at perihelion with the Earth's axis pointing towards the sun, and the obliquity is at a maximum. This is a synchronization. These synchronizations occur across this. And there are other synchronizations. For example, there's synchronizations where the precession is a maximum and the obliquity is a minimum. But these are rare. They don't occur frequently. So you can wind up in rare configurations, for example, where today the Earth's axis is pointing towards the sun during the summer solstice at aphelion, but the obliquity angle is headed towards a minimum, which means that there is less sunlight reaching the northern latitudes. You can also wind up with a configuration where 11,000 years ago, the Earth's axis was pointing towards the sun at perihelion, and it was at maximum, the obliquity is at maximum deflection, which means that the intensity of the sunlight is at its maximum at northern latitudes. The basic message in all of this is that the obliquity can diminish and enhance the effect of the precession index. And you'll see that come out in the model I'll describe. So if you want to understand insolation at northern latitudes at a qualitative level, this simple diagram here can give you an idea intuitively what's going on. So at the top here, this is a current situation, which I've talked about before. The summer solstice occurs at aphelion with the Earth's axis pointing towards the Earth, which means that the insolation is at a minimum. This configuration will change over 5,000 years, where the axis of the Earth will rotate so as to point towards the sun at a different point along the orbit. It'll get closer to the sun, and therefore, in going from top to this configuration on the right, the insulation increases. It will then rotate, the spin axis will rotate again, and in the future, 10,000 years from now, roughly 11,000, the Earth's axis will point towards the sun, which increases the insulation, and then it'll proceed to rotate further, a decline, and then it will go back to this configuration. So what I'm going to describe are calculations where I calculate the difference in the insulation between this configuration and that, and then I'll interpolate between the two. In other words, to sort of get a complete cycle. It's a smoothly varying function, but it's very difficult to do by hand, these calculations. So the model I'm going to describe, I call the partition model, has no adjustable parameters. It basically makes a hypothesis that the recurrence of the prominent features in the paleoclimate data are due to synchronizations. The model describes the insulation according to its physical nature, a wave. It's a time-dependent wave. It is a kinetic model. It just involves the Earth's celestial motions and the sun's rays. That's it. It has no aspect of the Earth's internal climate system in it. If you had to make an analogy, it's sort of like trying to describe the collision between two objects based upon energy and momentum. It's just basic kinematics, basically. I'll approximate the insulation by the product of the precession index and obliquity contributions. So the motivation behind this is that over a precession cycle, the insulation changes because of the distance that the sun is, the Earth's distance to the sun over a precession half cycle, which is comparatively short. The obliquity does not change that much over that period, as I showed in that graph. And it mainly deals with the angular distribution. It changes the angular distribution of the sun's rays. It doesn't affect the amplitude as much. And of course, the obliquity is over a longer time scale than the precession. So it's a slowly varying function. And so I will approximate the insulation by the product of a precession index contribution and an obliquity contribution. I'm going to focus on the fractional percentage change between successive mean daily insolation extrema, maxima and minima, at 65 degrees north latitude during the summer solstice. This preserves the timing of when these extrema occur, and it also deals with the trends in the insolation between them. And it's the trends that are important in terms of understanding certain behaviors. So here's the partition model. I'm going to discuss the mean daily insolation, which is commonly denoted by Q bar. So as I said, I'm going to approximate the mean daily insolation by a product of a precession index contribution A and a obliquity contribution B. And the mean daily insolation averages over a day, and the only quantity that affects that is the obliquity. That's the reason why there's a bar over the B. So now if I change the precession index contribution and I change the obliquity contribution by a certain amount, I can calculate the change in the mean daily insolation, percentage change or a fractional change, which is delta Q bar over Q bar. And that turns out to be the sum of a precession index contribution and a obliquity contribution if I ignore the cross terms. The cross terms are small. I demonstrate that in my paper. So you can ignore them. But what it says is that you can approximate it by a superposition of two quantities. So now I'll proceed to calculate the precision index contribution to that formula, the delta A over AI. And I'll calculate it between extrema. So this is a discrete calculation. In order to do that, I'll assume that the insulation falls off like 1 over r squared. And you can look up the formula for the distance at perihelion of the Earth from the sun. That's A, the major axis, times 1 minus the eccentricity at perihelion. Similar formula is for the distance at aphelion. You notice the eccentricity subtracts. In one case, it's closer. The ep is further away. So now you just do a simple algebraic calculation and you expand in a small quantity the eccentricity, and you see that you have a series like this for a perihelion to aphelion transition, which would imply that the insulation declines because at perihelion it's larger than at aphelion. So that's -2 times the sum of two eccentricities. So remember, I asked you to remember 0.05. So if the eccentricity doesn't change very much, that's 0.05 plus 0.05, which is 0.1 times 2, which is 0.2. So that's a drop of -20%. That's a large effect. And those correction terms improve upon that estimate. For a aphelion to perihelion transition, it's positive, as you would expect, with a similar dependence. And these quantities, the eccentricity that I've identified, EA and EP, are all obtained from Laskar's, Jacques Laskar's tool at successive extrema times. The obliquity contribution is much more complicated to determine. I do that in Appendix A of my paper, and I'm not going to go through it here. You really have to keep your wits about you in terms of calculating it. But the formula is given there. Phi is the latitude of interest, which, that's phi over here. Sine of phi, cosine of phi. It's the latitude of interest, which is 65 degrees north, which in radians is 1.134. The theta is the initial, and theta sub I and theta sub f are the initial and final obliquity angles. And HI and HF are what are called hour angles. These are related to sunrise and sunset, which are a function of the latitude you're at, as well as the value of the obliquity angle. For angular changes that are confined to a precession half cycle, turns out that the obliquity contribution can be well approximated by this simple formula, which is down below. It's kind of remarkable it is. 2 times the difference in the angles. Well, if you remember from that graph, I showed you how the obliquity angle changes over a precession half cycle. It's 0.005. So that gets to 0.01 or a 1% effect. Even if, which never happens, the initial and final angles are max 2.4 degrees, that's 0.042 radians, which is roughly, plugging that in with the factor of 2, that's 8%. But it never happens. It tends to be a fairly low amplitude effect. And again, the angles can be determined from Jacques Laskar's tool at the extreme times. So if I take the sum of those two contributions, the precision index and the obliquity, I add them, I can compare it with the actual numbers from Jacques Laskar's tool. So those are the blue dots, Jacques Laskar's estimates, and mine through the partition model are the red ones. What you see in between are interpolations between these points. Okay, they oscillate about 0 as you would expect. Okay, and you can do an error analysis if you'd like and determine the difference. And it's roughly about 1%. Okay, plus 1%, minus 1%. There's some deviations along 800,000 years of prediction, but it's pretty accurate, I would say. So now you can separate these two effects, partition, the precision index and obliquity contributions, into what I call a precision index wave and an obliquity wave. Okay? You see them there. The points in between are all interpolations. The accuracy of those is not really well known because the points are rather sparse over 800,000 years. So the points that are accurate are those that are indicated in those curves. It's the in-between that is more qualitative in terms of the changes that occur. The contributions obviously oscillate about 0. And the PI wave looks like, if you spend a little time looking at it, looks like a series of wave packets. It's an amplitude modulated wave with a envelope, which is basically influenced by the eccentricity, and a carrier wave that is precession carrier wave. The addition of these two gives you the total. And it also represents a superposition. So you can talk about these contributions in terms of wave language, if you'd like. So you can do a time series comparison of the precession index wave packets with the epicodome C data. So you can see the vertical purple lines which span the wave packets, and you can follow them up as to where they begin and where they end. And then you can look at the trends in the wave packets going up and going down, and how they coincide with temperature trends that you see in the data. It's not exact, it's rough, but qualitatively, there is a reasonable amount of consistency between the predictions of the precession index wave and that of the data. Timing isn't always exact, but it's pretty good considering the crudity of the model. So if you want to follow interglacial and glacial periods, you simply follow the wave packets. Now, if you look at these wave packets and you look at the one back here, which is associated with marine isotope stage 19C, that wave packet looks very similar to the one here, which is the Holocene. And I'll get back to that in a moment. So from this analysis, you can infer why it is that certain interglacials are wider than others. And it turns out they break out into two types. So if you look here at 19C, which I was just discussing, it starts on the red side, red meaning going from cold to hot, and then the green side going to cool. It subtends one precision index cycle. Right? And coinciding with that is an approximately synchronized obliquity wave cycle. So its width is basically determined by one precision index peak. If you go over to a wider one, which is right over here, you can see it's subtended by two such peaks. The same is true here, which is the one that people usually associate with the Holocene. It's a 2 precision index peak. And the Holocene is a 1. So the Holocene is a type 1 interglacial. There is the very narrow peak, 7E, which I will show in a moment, results from an out-of-phase relationship between the obliquity wave and the precision index. So that basically classifies the types of interglacials and how they depend upon the underlying celestial motions. All terminations, if you go through and do the entire analysis, will always coincide with a precision index wave and obliquity wave that are both negative, meaning that they're in decline. The trend in insulation is in decline, with the minima approximately synchronized. It's not exact. It's crude, but they're approximately synchronized. So now, what about the narrow type 1 interglacial 7E? Well, if you look at the underlying behavior of the precision index wave and the obliquity wave, you see that the obliquity wave increases as the precision index peak increases, but then it goes out of phase and cuts it off. The obliquity diminishes the impact of the precision index peaks and cuts it off. And that may account for why this one is so narrow. It's not exact, but qualitatively would appear to be consistent with that peak being narrower than others. What's wrong with this approach? Well, there is a problem. So if you look at the interglacial inceptions, there are delays that occur. You can see it here. The red line here corresponds to where the precession index peak and the obliquity are synchronized. But there's a delay in that inception, although the termination corresponds to a synchronization of the obliquity minima and the precision index minima. There's a similar kind of delay that occurs here. And at one point, I sort of said, well, everything I've done here is probably a fluke, and then I find out, this and bothered me. So I began searching to see if anybody else has said anything about this. Well, turns out that you can find a paper where the epicodome C data is compared with benthic data, which corresponds to deep ocean cores, where they measure the oxygen 18 to oxygen 16 ratio. It's referred to as LRO4, named after the authors that did this analysis. And there's a paper by Frederick Perrin and others where they compare these two. And what they find is timing discrepancies between the benthic LRO4 data and the epicodome C. And when I looked at this, I said, it's really curious. They occur precisely where my model doesn't work. So you can see the green, this is a plot, by the way. It's the reverse of the plots that I have. Goes from 0, which is present on the left, to the future, which is on the right. And what you see is a difference analysis represented by this green line, which corresponds to the deviations from synchronization of the two data sets. And you see that the largest ones tend to occur for the marine isotope stages that I have a problem with. So I don't know what the resolution of this is, but this goes back to Feynman's statement of the scientific method. It relies heavily on reliable data. So the question then becomes, is the data reliable? I don't know. I mean, I'm not an expert in this area, and even if I was, I wouldn't consider myself to be an expert anyway. It's something that is outside my ability to comment on. I can only look at what the analysis shows, and it seems to indicate that there are timing delays, timing discrepancies between the two sets of data, and curiously enough, they occur in the same aspects of my model. You don't have to go far, by the way, to find discrepancies in the ice core data. So, for example, if you go to a NOAA site, which I indicated on an earlier slide, where I got the Antarctic data, you can find a set of data called Vostok, which is a different part of Antarctica, where they looked at ice cores. And you can see here that there are timing discrepancies between the two sets of data from present 0 to minus 450 years ago, 450,000 years ago. So the timing issues are important to resolve. So the title of my talk was Estimating the Termination of the Holocene Warm Period. And it turns out you can do that from the work I've done with this model. As I said, MIS 19C, which is back 778,000 years ago, is similar to marine isotope stage 1, which is the Holocene. They're both of type 1, and you have to define what termination means. So the definition I use is the termination period is from the PI wave maximum to the approximately synchronized minimum. And the case for the correspondence between marine isotope 19C and marine isotope stage 1 is somewhat compelling. The underlying behaviors of the precession, the obliquity, and eccentricity are similar. Also, the change in the insulation from peak to the termination was also similar. So in the case of 19C, the drop is 48 watts per square meter. In the case of MIS1, the Holocene, it's 50 watts per square meter. That's from peak to the minimum. The termination for MIS 19C is 10,500 years based upon that definition. And for the marine isotope stage 1, the Holocene, it's 11,600. They differ by 1,100 years. And the reason for that is that if you look at the precession index carrier wave cycle, it's longer for the Holocene. So you can make an estimate. And the plot I have here is mean daily insolation for 65 degrees north latitude during the summer solstice. It ranges from going back 1,000 years and forward 1,000 years. The vertical black line here is 0, where we are today. And the minimum is here. And if you look at that, it's about 450 years it occurs, so you round it off to 500. The other thing you notice is that the minimum here is really very shallow. It'll only change within the next 900 years by 0.15 watts per square meter. It's hard to imagine that that's going to amount to anything. But anyway, the estimate I have is 500 years. The problem is, what is its specific mechanism within the Earth's climate system that causes the descent? This doesn't deal with it. That has to do with the fundamental understanding of the Earth's climate system. How does it respond to it? And of course, if you believe that this has something to do with what's going on at northern latitudes, then you should be looking at actually the most extreme weather on the planet, which is at the northern latitudes. That extreme weather at the north, around the North Pole, is a gigantic cyclone that's about the size of Asia. And it's there largely or primarily for two reasons. One is the Coriolis force, which is a non-inertial force that, because we're in a rotating frame, increases as you go further north. And what decreases, of course, is the sunlight towards those northern latitudes. This gives rise to a rather large cold air reservoir. And of course, as the insolation decreases over a long period of time, in our case, in the Holocene, that's about 11,000 years or so, that cold air reservoir likely increased. And so if you need to look at a culprit in all of this, it's probably what's going on in that region. However, we don't really understand that region very well. Goes under the name sort of generally as the polar vortex. And it's this gigantic cyclone that's kept in check by the jet stream, which separates the cold air from the warm air. And during the summertime, the temperature gradient between the north and the south, northern latitudes to the southern latitudes, is comparatively low compared to what it is during the winter. That gradient increases, and during those periods, the jet stream makes excursions south where warm air can mix with cold air, creating snow and ice, for example. What's also interesting is that this polar vortex region can go unstable, and you can see it there off to the right. This occurs over a period of months where it is incredibly interesting and beautiful behavior, but understanding it is something we really don't quite understand very well. And in order to be able to predict what this might do over a long period of time is a challenge. Does it average out to zero? In other words, it has no effect at all. Or does it have an effect that will cause more snow and ice to accumulate around the Arctic Circle and increase with time? And until we understand this and how the insulation couples to it, we're sort of guessing. You'll spend a lot of your time telling stories, but I believe the only way you're going to get at this is that you have to go back to the scientific method as described by Feynman and convince yourself that you really understand it. Okay. So anyway, these are the results of a simple model. That's a kinematic model. If you want to understand the recurrence of interglacial and glacial periods over the last 800,000 years, then you just follow the precision index wave packets as I described. The paleoclimate temperature trends follow rising and declining trends in the PI wave packets. The interglacials fall into two types depending upon the number of precision index peaks that subtend them. Interglacial terminations occur more or less in pretty much the same way, with approximately synchronized O-wave contributions. And the inceptions coincide with approximate synchronizations of the P wave and O waves. And there are two exceptions, and those are also evident in paleoclimate data comparisons. The one general conclusion that I think is irrefutable in my analysis is that the precision index has a much more significant impact on the paleoclimate data than the obliquity. There are a lot of papers that are out there that claim the reverse, but I think I'm convinced that the precision index is much more important than the obliquity, although the obliquity does enhance the precision index effects. And I don't know if this will work. I don't think it'll work. Let's see if it'll work. Synchronization. It's a remarkable phenomenon. You can start these out of phase, and over time, short period of time, they eventually begin to become synchronized. They settle into a natural frequency. Of course, if you disturb the cans, you'll knock them out of phase again, and they will go through another cycle. So anyway, I think I'll stop here. And thank you all for listening.
On your slide number 25, when you're talking about Holocene termination estimation, what are you predicting for the next 900 years? You say insulation is only going to drop by 0.15?
Yeah, I'm predicting that the termination will occur within 500 years. In other words, there will be a gradual accumulation of snow and ice at the northern latitudes. And likely by 500 years, you'll start to see this significant drop occurring, and it will proceed to continue and continue over time and put us into a glacial period. But it's at the midpoint where see where the minimum is right here? That minimum occurs at about 450 years in the future. So I rounded it off to 500. And so that's the basis of the prediction. That's where the precision index minimum and the obliquity minimum coincide roughly. So as to whether it will happen or not, I don't know, but that's what the model would suggest. Does that answer your question?
It does, yes. Do you have any comment on the work of Carl Otto Weiss? He talks about various solar cycles lining up, et cetera.
Yeah, well, I had a friend of mine the other day who called me, wanted to talk about this. He's a big enthusiast for all of this. And the only way I can answer all of this is you have to go back to the scientific method. The scientific method tries to relate cause and effect, right? So if somebody says, well, look at this solar cycle data, and then look at these measurable things, it looks like they're correlated. Well, I don't know. Have you ever gone to the site Spurious Correlations?
Yes, I have. Yeah.
Okay. So, the question is, what is the causation? What you have to connect them somehow in order to convince yourself that you have some, predictability of some kind, like I've done here. Okay. I've tried, but, there's a big hole in what I describe here. And that is, what is the response of the Earth's climate system? Until you get at that, you don't have a convincing scientific method approach to this, right? So, and I've seen data, for example, solar irradiance changes over time, and Arctic temperature, average Arctic temperature over time. And, they kind of follow each other, right? But if you look at them very carefully, you notice that there are delays. And if you plotted the delays as to when the features occur that you say are correlated, you'll find out that there's significant discrepancies in time. And so, but the question is that real? In other words, is there some physical effect that causes that? Or is it just spurious? I don't know. So, what they're claiming may be true, but I sincerely doubt that changes in the solar irradiance caused by sun cycles is responsible for ice ages. I don't believe that's the case. Now, could those changes enhance the likelihood of an ice age? Well, possibly, yeah. I mean, you can come up with a story, that moves you in that direction. So if you say, well, the cosmic rays are responsible for seeding clouds, for example, and they enhance cloud formation. So that occurs when the sun is less active, right? Fewer sunspots. And cloud formation is important in terms of cooling, right? It also participates in heating as well, but it participates in cooling. So you can imagine that if those cycles coincide with this cycle I'm talking about, there could be an enhancement. But, you have to come up with a theory, a predictive theory that can shed light on that in some way that's very convincing, and so, we get into these, what I call arguments of ignorance, arguments from ignorance, because there's a gap in our understanding of something, technical understanding of something. People get into these arguments about, well, I think it's this, no, I think it's that, and it goes back and forth forever. The only way to get around this is using the scientific method. Now, some people will tell me, John, you're asking for too much. I mean, this is too hard. It's always hard. What makes anybody think that acquiring knowledge is easy? Puzzles have existed about the nature of how the natural world works for centuries. And it's taken centuries to resolve some of these things. And very often what happens is some person with a unique insight into something comes along and can see through what everybody else is confused about and comes up with the hypothesis and a theory that works in terms of explaining what's actually going on. It revolutionizes our way of thinking about how the natural world works, and that has a tremendous impact on human imagination, because you can now think of things that before were not possible that are possible, and then things that are feasible, and then practical. You can transform history, through this. But, it's always hard. Every major scientific discovery that I can think of was extremely difficult and took centuries to resolve. And this should be no different. In fact, it's really hard because the Earth's climate system is so complicated, and there's so many overlapping time scales and spatial scales. It's hard to sort out what's going on. So there may be some validity to the solar cycle, but I don't have a clue on how to connect the cause and the effect from a theoretical standpoint. Trying to predict clouds, for example, is extremely hard. And if you don't have that part of theory right, in understanding the Earth's climate, that's an error that you have in it. Whatever models you have, that's an error, and that error propagates. And you can't estimate it, unless you really have a good understanding of the actual physical phenomenon. So I don't know if that answers your question, but
I think it does. I think what I'm getting is that Earth's climate is very complex, and probably a lot of things do affect it on very short time scales, but that's not what you're talking about in this presentation. It's on bigger time scales, right?
Yeah, the time scales are different, but you have to understand that the effect I'm talking about has been acting for 11,000 years. So it's acting now, and it has been acting, and there's some effect that's had on the Earth's climate system. And so it will continue to have an effect as we go into the future, so that's basically it, but I can't predict with any confidence, or at least enough confidence. I can only tell you what this model says about the Holocene termination estimation. It could be right. It could be completely wrong. I'm not going to know. None of us are, because it's too far out, but the effects might start occurring. It's possible. You have to monitor snow and ice accumulation in North America and Greenland, for example, to see how the trend is and whether that trend is going up, down, and over what months of the year, and so we're in a state of uncertainty. That's all. That's basically it. So.
Any other points you'd like to make before we go ahead and wrap up?
No, I think, I thank everybody especially you, Tom, for inviting me to talk about my work, and I thank people for having the patience to listen.
All right. Thank you very much. I really appreciate it. Talk to you later.
Welcome.
John Parmentola. Yeah. Goodbye.
Yeah, bye.